So now let's actually go back and see some of those proportionality constants, right, and what units they have. Okay. So remember that I called the constant 1 over square root of LC as V, right, which is actually the velocity of the wave in the original wave equation. Remember, L's and C's in our model are distributed values, right, inductances per unit length and capacitance per unit length. So if I wanted to find the units for this, right, so inductance obviously is measured in henries and capacitance in farads, right. So but those units don't immediately lend to something that we can simplify. So we'll always go back to the toy models for inductors and capacitors, right. So remember that we had V is L di by dt, right, where L was the inductance in henries, right, your toy model for inductor. So I can say the units for L is essentially volts, right, divided by di by dt, right, which would essentially tell me this is amps per second. Okay, so voltage divided by amperes per second is another way to give the units for inductance, right, or Henry. So let us use that and see what we get. So we are going to do volt per ampere times second. Okay, this is for the inductance. So similarly for capacitance, we have I is C dV by dt. So units for C is essentially amps per volt per second. Right? Okay, so that I can write here. So some of the astute audience must have caught me, right? So remember L and C here are inductances per unit length, right? So we'll also have a meter per meter. Okay, so it's not just henries, but it is Henry per meter, right? And similarly, we have farad per meter, right? So now you can see that the amps and the volts cancel off, and we can see that the meters and seconds multiply together. I'll get second square per meter square and under the square root, so it becomes seconds per meter, and you essentially find that the units are meters per second, right, which is essentially the quantity for velocity, right. Now you can see why we actually associate 1 over square root of LC with V or velocity, right. This is the speed with which the voltage and current is propagating along the transmission line. Next, this special term Z naught, right, for now is just a constant, seems to be related to L and C, right, as square root of L by C. And if I were to look at the units for this, doing the same exercise, I have volt second per amp meter, right, and then I'll have to flip for capacitance. So I'll have volt meter per amp second. This time the meters and the seconds cancel off, right? And voltage divided by current is resistance, right? And so this is actually the units of ohms, right? So V has the units of meters per second, and Z naught, a constant that is required to essentially establish the functional dependence of current, right, given the functional dependence of voltage, right. So once we get the form for voltage as V plus plus V minus, when I extract the value for I from the telegraph's equations, I actually have a certain constant Z naught that seems to appear, right, and the units for this Z naught is ohms, right. So the picture on the top is essentially to say that the transmission line has been modeled as a sequence of LC circuits, right. Okay, so remember this L and C is in our model, right? But if someone were to give you a cable, it's unlikely that the manufacturer will actually give you L's and C's, right? Instead, what they'll actually give you is the Z naught that we saw in the previous slide, right? It also comes with another popular terminology called the characteristic impedance. Okay, I'll reserve a discussion on what is characteristic impedance a little while later, right? But for now, this Z naught value, which seems to be in units of ohms, is a number that will be specified by any cable vendor, right? So if I go buy cables, they'll actually specify the characteristic impedance. This is one of the metric. And in places where the delay effect, right, this retardation effect that we are studying is important, they'll also give you the speed of light delay of the cable, right. That is, if I were to excite some signal at one end of the cable, how long does it take for it to reach the other end of the cable, right. So these are the ones that I can actually measure. This is why these are the quantities that the vendor will give you, right. So L's and C's are harder to measure, but characteristic impedance and speed of light delay are something that I can readily measure in labs using experiments, right. So given a cable, I'll normally be given two parameters, tau and Z naught. Sorry, not tau. Tau, let's not confuse with the tau that we introduced earlier. That's why I use TD, right? So TD is the speed of light delay of the cable and the Z naught, right? So of course you can measure the physical length of the cable, and the length of the cable L divided by the speed of light will give you this TD as well. So I have not used the small c, which is used for speed of light, because sometimes we can use dielectrics in these transmission lines, cables, so that the speed of light, because remember that speed of light is essentially 1 over square root of mu 0 epsilon 0, which is the permeability and permittivity of free space, right. But if I were to introduce a dielectric, the relative permittivities and permeabilities will come in, and the speed of light slows down, right. So you can anticipate that some transmission lines that have a dielectric spacer between the conductor, that the speed of light is not quite the 3 times 10 to the 8 meters per second that we are aware of for the speed of light in vacuum, but rather we call this as the speed of light delay in the cable, right. So remember, nothing can move faster than the speed of light in the medium, right. So given that you are told only the speed of light delay of the cable and Z naught, how can I get to the L's and C values, right? So the L and C are my model parameters, but nevertheless I would like to get from the speed of light delay and Z naught that they give me to the L and C values, right? So what can we do? So TD is essentially L by V, but V was 1 over square root of LC, right? LC as in our toy model for the transmission line. Similarly, Z naught was square root of L by C, right? So if I were to take the product of TD and Z naught, I essentially get L times capital L, right? So I can always go for a given cable whose length, speed of light delay and the characteristic impedance are known. I can essentially estimate L by just multiplying TD Z naught and dividing it by L. And how would I get capacitance? I would have to divide, right? So if I took the ratio of TD to Z naught, okay, you will notice that I can extract out the capacitance, which is to say that TD is okay. So remember that L and C are distributed inductance and distributed capacitance respectively, right? That is why you are noticing the L in the denominator, right? So you can also estimate the net inductance, right? So if I want to call out specifically on the total inductance, right? Even though it is not a lumped element, remember that the transmission line or the cable is not a lumped element anymore, right? Depending on the frequency of operation, you might have to break them into these distributed circuits. Nevertheless, if I wanted to know what is the net inductance from end to end of the cable, you can just multiply by the small l, right? And you would just get TD times Z naught and then the C total as TD by Z naught. Okay. The reason to do the exercise in this particular slide is so that you are comfortable that regardless of how the transmission line is specified, right, which most commonly is specified using the characteristic impedance and the speed of light delay, you should be comfortable in going to the distributed model in estimating what the L's and C's are, right? Because remember that the solutions for the voltages and currents are functions of t and x, time and distance, through the appearance of square root of LC, right? So L and C are critical in order for you to make estimates on voltages and currents, right? Okay. Now that we have looked at the transmission line, we want to now put the transmission line in a real circuit, right? So let's recall the circuit in lecture 2 of this week, right? This is perhaps the simplest circuit, right? So I have a voltage source, a time varying voltage source, and then I use a cable to connect to the load RL, right? So the source, voltage source, might have impedance looking in, right? And the load also is being approximated as a resistor here. We'll soon show that this can be extended to other kinds of complex impedances, but for now, for the discussion's sake, this is the overall circuit, right? So remember that studying the transmission line in isolation is not that useful, right? So we want to see the transmission line in the context of real circuits. Right? So now when I start to attach loads, right, now these loads are lumped loads. Okay, this could be one of those lumped elements in your circuits, right, where the resistor size is extremely small compared to the wavelength, right, of this particular circuit problem. But the transmission line's length is not negligible, right? It can be several feet long to maybe even meters long, right? So we want to know, when I excite the voltage at the source, what does this transmission line do? How do these voltages and currents interact with loads, right, at the opposite end of the transmission line? I also want to do this as an exercise so that you are comfortable in handling voltages as a combination of this V plus and V minus functions, right. So let us take this as an exercise to actually see how voltages and currents in the transmission lines can actually be used in practical scenarios, right. So remember that this is our model for the transmission line, right. So at any point along this transmission line, right, remember I can associate a certain voltage and a current flowing at that particular location, and these voltages and currents are of the form V plus plus V minus, and current is of the form V plus minus V minus by Z naught, right. So let us see how we handle these situations. So I am going to say this is the left side and this is the right side. On the right side we just have a lumped load, right, RL, where our Ohm's law is satisfied, right. So the voltage across the resistor divided by the resistance RL gives us the current flowing through the resistor. So this is fair enough, right. But the left side is where the transmission line ends, right. So we want to know how to deal with, right, the voltages and currents on the transmission line. So on the left we say that the voltage, right, is essentially V plus plus V minus. Okay, we are not yet associating any particular form for these functions, right, V plus and V minus. It could be a pulse of voltage, it could be a continuously changing voltage, right, it can be anything. And we have the current, which is essentially V plus minus V minus by Z naught, right. So this is the voltage and current on the transmission line, and the voltage and current on the load is quite simply, we are calling it VL, and I is IL, which is VL by RL, right. So all you have to do is simply equate, right, a particular location, which is the bridge between the resistor and the transmission line, can only have a unique voltage and a unique current flowing, right, at that particular point. So we will just say that the left hand side and the right hand side, the voltage and currents have to be the same. So we say that V plus plus V minus is equal to VL, and V plus minus V minus by Z naught is equal to VL by RL. Okay. So remember that V plus is what is given at the source, right. So that voltage is slowly propagating from the left to the right, right. So this V plus in some sense should be known. We will see how we will find out V plus, but it's essentially, this exercise is to find out what V minus is, right. So as this voltage approaches the load and meets the load, we want to see if there is any voltages and currents now moving back along the transmission line, right? And if so, how much, or how much current is going back. Okay, so we are in the exercise of finding V minus, find V minus given V plus. Okay, so we are going to introduce a new variable gamma, which is called the reflection coefficient. Which is essentially V minus by V plus. Okay, it's a ratio. It's the ratio of V minus to V plus. Okay, so V plus is known, right? Which means that if you give me gamma, I can find out V minus, right? It is a stand-in for V minus. Right? So we'll eliminate VL from this pair of equations. So we essentially get that V plus plus V minus is equal to RL by Z naught times V plus minus V minus. Okay, if I were to divide by V plus on both sides, this essentially gives me 1 plus gamma is equal to RL by Z naught 1 minus gamma. You can solve this to get gamma is RL minus Z naught by RL plus Z naught. Okay, I will leave this small derivation, simple linear algebra, just rearrange, bring all the terms with gamma on one side and you can get this expression. Okay, so what is this expression trying to tell you? That if there was some voltage that appears to be moving, right, from left to right, right, because I incident a voltage from the source on the left end of the transmission line and it is moving at the speed of light, right, to the right of the transmission line, right, this voltage that appears to be moving, right. So when I say voltage is moving, just think of it as the voltage is appearing. What appeared at the beginning of the transmission line at some time t appears later at the end of the transmission line at a later time, right. So this voltage moves along the transmission line till it reaches the load and some portion of this voltage, right, seems to be returning back. Okay, that is why we call this a reflection coefficient. It is almost like you throw a ball at the wall and the ball comes back, right. So the entirety of the ball comes back, right, and we'll actually see two special cases, right, which is when the load RL is 0 and infinity. These two correspond to what we call short circuit and open circuit, right. So looking at the expression for the gamma as a function of RL, can you quickly tell me what gamma is for RL equals 0? Yes, it's minus 1. And gamma for RL equals infinite or very large and open circuit is essentially 1, right, because as RL becomes extremely big compared to Z0, you can sort of ignore Z0, right? So you basically have an RL by RL kind of expression. You essentially see that the gamma becomes 1, right? So I'll try to give you some analogy for this in the next class. But this is to say that when you send some voltage, right, from the left hand side, right, of the circuit at one end of the transmission line, the voltage appears to move to the right up, and then when it meets the load, there is some fraction of that decided by this ratio RL minus Z0 by RL plus Z0, and that fraction actually comes back. Okay, there is a very special case, right, which is when RL becomes equal to Z0, right. So when RL becomes equal to Z0, the reflection coefficient gamma becomes 0, right. And in fact, it is a very popular way to actually try to understand what characteristic impedance is. So remember, Z0 we said was square root of L by C, right, it was just a proportionality constant till the last slide. But if someone were to ask you what is this characteristic impedance, you can actually say it is an equivalent resistor of value Z0 when placed at the end of the transmission line, causes no return voltage signals or no reflections. Okay, so for high frequency voltages that are launched along a transmission line, the resistance, the real resistance, right, a real load applied at the end of the transmission line, when the reflection turns to 0, that value of the load, right, in ohms is the characteristic impedance of the transmission line, right. So this is one way and a very useful way to understand characteristic impedance of the transmission line.